Because condition variables and condition objects are more complicated than reentrant locks, we're going to talk about a couple of other things before we get into the structure and functionality of the class itself. There isn't much sense in trying to understand the API until you really get a good grasp of how the various pieces work together, because otherwise it just gets confusing. So I'll talk about a couple of common use cases where condition variables are applied in practice. So as you will see, or as you may already have ferreted out, condition variables are very powerful, but they can be a little hard to understand and apply correctly. And the reason why that is the case, the reason why it's hard to understand them, is because they require several moving parts in order for them to be understood and applied correctly. And this diagram is from the book I wrote on pattern-oriented software architecture, and it kind of shows how they work at a high level. So let's kind of talk this through. So what you got here is we got two threads, client thread 1 and client thread 2. We have something called a monitor object, which is the common higher level pattern that condition variables are usually applied to implement. And then we have a monitor lock and we have a monitor condition. In practice, for these types of things, you'll often see that you have more than one monitor condition, but let's just keep one for now. So the way this is going to work is, and let's say for sake of argument that this is going to implement some kind of a bounded blocking queue. So it'll be a blocking queue, and let's say that sync method 1 is something like the get method. So we're going to assume that our bounded blocking queue starts out empty, and client thread 1 is going to call sync method 1, which for sake of argument, without loss of generality, will be the take method on a bounded blocking queue. So we come in here, we call take. The first thing that we do is we acquire the monitor lock. And let's say for sake of argument, there are no other threads that own it, so we get it right away. We then go ahead and do some work. And let's say that as part of that work, we check to see whether or not the queue has anything in it. And of course it doesn't, because it's the first time we call get or take. And then as a consequence, we have to wait on a monitor condition, and that monitor condition would be the not empty condition. So we're going to wait on the condition not empty. What that does, as it says here, is it automatically releases the monitor lock and puts the thread to sleep. So thread 1 is now asleep, and the lock is released. Thread 2 comes along, and it's going to call another sync method. In this case, it's going to call put. And that's going to go ahead and try to put something on the queue. So what it's going to do here is it's going to come in, it's going to try to acquire the monitor lock, which it will get because, of course, nobody else is owning it at the moment. The other guy's asleep. It then does some work, which in this case would involve putting a message onto the queue. And then it goes ahead and it notifies the not empty monitor condition that there's something on the queue. And then thread 2, client thread 2, releases the lock and goes on its merry way. At this point, thread T1 is reawakened, and the operating system or the thread scheduling package reacquires the monitor lock, which is not in use by anybody because this thread had released it. And then we go ahead and do some work, and what that work's going to do now is it's going to find that there is indeed a message on the queue, and so it'll go ahead and consume that message, which it'll return back to the caller, and then it'll release the lock on its way out. Now here's where things get interesting. It might turn out that, I don't show that in this particular diagram, but it might turn out in practice that there's another client thread 3, and between the point when thread 2 released the lock and the point when thread 1 was reawakened to acquire the lock or to try to acquire the lock, client thread T3 could sneak in there, grab the lock, and dequeue the element off the queue. And if that was to happen, then when thread 1 reacquired the lock, it would go and discover, aha, there is nothing on the queue, and it would have to turn around and go back to sleep again like it did up here by going back into wait. And that is sort of underscoring the fundamental non-determinism of concurrency, which can throw you for a loop, no pun intended. And that's one reason why you typically use loops when you're checking these conditions, because it may turn out you don't get your condition satisfied even though you were signaled or notified by somebody. Okay, so that's the point here, that the non-determinism of concurrency can be rather tricky. And therefore we always have a loop. And if you want to read more about that, there's a nice Stack Overflow article here that talks about why you should do this. And I'll talk in detail later about some situations under which you don't, some other situations under which you don't get your condition is satisfied even though you were signaled. As a consequence of all this, people very rarely program to condition variables directly, but instead you hide them behind some other abstraction. For example, in your assignment to B, you will hide the use of the condition object behind a simple semaphore class with its methods acquire and release. So under the hood, the acquire and release methods on the semaphore class, simple semaphore class, will use condition objects, but you won't expose those directly to clients. And that's a very common practice. Condition variables form the basis for a number of higher level synchronizers in the Java class library. So for example, blocking queues like array blocking queue and linked blocking queue and various decks in the Java util concurrent packages use condition objects to do their thing. And we'll talk about this a little bit later when we look at the implementation, because I'll show you how a pair of condition variables are used, or condition objects are used, in array blocking queue. Java's built-in monitor objects also support condition objects. There's one condition object per monitor object, and we'll talk more about that. And of course, the most common use is in the context of something called the monitor object pattern, which is one of the POSA2 patterns. You can read about it here. And that basically describes how you encapsulate an object using the monitor object pattern so that we have these synchronized methods, and those synchronized methods ensure only one thread is able to have access to the state of the object at a time, and the threads can coordinate their interactions by basically waiting and signaling each other when conditions don't satisfy their needs, their intents. Okay, so that's the end of the discussion of the common use cases. With that out of the way, now we're going to be able to turn our attention to actually how the condition object works. But it's really important to get that big picture view. Otherwise, the interface doesn't seem to make much sense because it's very simple, but it's doing lots of powerful things.